Okay, guys, we're going to go over our warm-up, but before we do that, the assignment that you have for homework today, 601.3, work energy theorem problem set, it's going to have similar questions to what we're about to do in the warm-up, so this will also help you with that. It's going to help us segue into our notes today on work energy theorem, and this question, as well as the ones we're going to go over in our notes today, are similar to the types of calculations that you're being asked to do in the extension section of the RA from last week. Okay, so all of this stuff that we're about to talk about with the warm-up and the notes should help you both with today's assignment and with your RA, and obviously in preparation for your test next week. So the warm-up question says a 0.071 kilogram paper cup falls from a 0.78 meter high table. If there is no air resistance, what is the change in kinetic energy of the cup? And then what causes this change in kinetic energy? Okay, so when we approach this problem, you need to label the things that we know. We know that we have a mass of this cup that is 0.071 kilograms. The question says that the cup falls, and that's going to imply that it falls from rest. Okay, it's implied there. It doesn't say that it's thrown or knocked off or anything else. So the initial velocity of this cup is 0, and then it falls, and as it falls, it's going to fall 0.78 meters. So I know the displacement will be negative 0.78 meters because it's falling downward. Okay, and there's no air resistance. So I know that this cup, when it falls, it's going to accelerate. Does anybody, or who can tell me what the rate of acceleration will be? 9.8. There you go, 9.8. It says no air resistance. This is a free fall scenario. The acceleration of this cup will be negative 9.8. It's negative because it's toward the ground. It's going down. Okay, and that's all the information I have. Okay, I know that I'm trying to find the change in kinetic energy, and I know that my cup initially has 0 kinetic energy because it's initially at rest. So in order for me to find the change in kinetic energy, I just need to figure out how fast that cup is going at the end. I need its final velocity, because once I know the final velocity, I can find the final kinetic energy and thus the change in KE. Okay, so this is very similar to problems that we did last week. With the information I have, which is mass, initial velocity, displacement, and acceleration, I can find final velocity. And I'm not going to use the mass for it. I'm going to go all the way back to my kinematic equations, this one specifically. Vf squared equals Vi squared plus 2 times A times delta X, because that's the stuff I have. Here's Vi, here's A, here's delta X, and I'm looking for Vf. Is there more than one way to do this problem? Yes. You do not have to start here. In fact, you didn't necessarily have to use this equation at all. You could have done it a different way, and that is perfectly fine so long as you end up in the same place at the end. There is more than one way to solve most of the problems we're doing now because we have so many formulas that we can use. Okay, but depending on the information I give you, sometimes one of those is easier than others. And this, in my opinion, is the easiest way to go for this problem. So let's go ahead and substitute in. Vf squared equals 0 squared plus 2 times negative 9.8 times negative 0.78. That 0 squared, I'm just going to cross through that. So I'm really just multiplying 2 times 9.8 times 0.78. Those negatives are going to cancel. That leaves me, bless you, with Vf squared equals 15.288. Again, that's Vf squared. I need Vf. So I need to take the square root of both sides. The square root of 15.288 is plus or minus 3.91 meters per second. Okay, that is plus or minus when you take the square root of something. Can anybody tell me why I chose minus? Why did I choose negative 3.91? Because it's falling down. Yeah, perfect. Falling down. So I chose the negative sign because I know that it's going to be negative. But if you're in that situation and you're taking the square root, you do need to figure out, based on the scenario you have, is this positive or negative? In my scenario, based on the way that we define that direction down as negative, this would be negative 3.91 meters per second. That negative sign's not going to ultimately matter because when we solve for kinetic energy, it's scalar. It doesn't have direction, and you'll see that when we use this equation. Again, Final velocity is not what we're looking for. We want change in kinetic energy. My initial kinetic energy was 0. My final kinetic energy I can calculate, 1/2 mv squared, and that's what we're going to do. We're going to substitute it in, and here's what I meant. When I square this negative number, that negative sign goes away anyway. Okay, so I have 1/2 times 0.071 times 3.91 squared. Again, that negative goes away as soon as I square it. And that leaves me with kinetic energy of 0.543 joules. So that's my final kinetic energy. My initial kinetic energy was 0. Now I have 0.543 joules. I have added kinetic energy. Well, it wasn't me. Okay, something added kinetic energy here, and so we have more than we started with. In fact, our change in kinetic energy, which is what the question asks, is positive 0.54 or 0.543 if you want to include that extra decimal joules. Okay, so that's the first part of your warm-up. The follow-up part, and I kind of mentioned it a second ago, where did that energy come from? Why does my cup now have 0.54 joules more energy than it did before? Obviously it sped up, that's why, but why did it speed up? The velocity changed. Why did my velocity change? Gravity. Ultimately, it's that force of gravity. Okay, that force of gravity does work on the cup. Remember work? We talked about that before, the first couple days of this unit. Gravity does work on the cup. Anytime you have a force causing a displacement, which is exactly what the gravity did, it pulls down on everything, including that cup. Okay, that force times that displacement, that gives me the work. And so gravity can do work. Gravity makes things speed up. It does positive work on things when they fall. Okay, if they're just falling down from rest, it's always going to give us positive work. Okay, friction can do work. Friction does negative work on things. You and I can do work depending on if we're pushing or pulling something to make it speed up or slow down. But in this case, gravity does work and it adds energy to that system. In this case, that system being the cup, causing the cup to gain kinetic energy. That's the other part of your warm-up. And that also leads us into our discussion today, because our discussion today is on the work energy theorem, which was introduced in your lab, because this is very similar to your lab. In your lab, though, it wasn't gravity doing work, it was a fire extinguisher. Okay, but you had a force applied for a certain distance that caused a change in energy. Same thing. Okay, and that leads us into this. So work energy theorem, which was introduced in your RA, states that the net work done by the sum of all forces acting on a system equals the change in kinetic energy of the system. As a reminder, net work is the total work on your system. So in my previous example, there was only one thing doing work on that cup. Gravity, that was it. So that was my net work. But I could have just as easily given you a scenario where gravity did work, causing the cup to speed up, but there was also air resistance working against it, causing the cup to slow down from however fast it would have been otherwise. Okay, and so you could have more than one force, and thus you could have more than one thing doing work. And if you do, you have to find net work by adding those things together, keeping in mind that work can be positive if it's adding energy to the system, or negative if it's taking it away. So you have to add those together, but keep in mind the sign, okay, depending on whether you're adding or removing that energy. Or the way we define positive and negative energy initially was if the force is in the same direction as the displacement, or some component of it is in the same direction as the displacement, that's positive work. And if they're opposite, that's negative work. Same thing. You could use that too. Okay, but whenever you actually use this in our equation, because the equation says, hey, this net work equals the sum of the force, equals the change in kinetic energy of the system. So this is what the actual work energy theorem equation looks like. It says, hey, you have initial energy plus whatever net work is done will give me your final energy. Or you can rearrange this equation. If you subtract initial energy from both sides, then you have net work equals EF minus EI, final minus initial energy. And anytime you're doing final minus initial, that's change. So you could shorten it and write it like this. The net work acting on a system equals the change in energy of that system. And that's what that says up there. Okay, it says the net work done by the sum of the forces equals the change in kinetic energy of the system. So this is your work energy theorem. And if I ask you for an energy transfer equation, I'm asking you to use this equation down here. You'll see that in your assignment today. All right, so let's take a look at the work energy theorem with our warm-up question. We already determined the change in kinetic energy of the cup. Let's find the work done on the cup, because we can use that equation we just learned. Initial energy plus that net work equals final energy. And guess what? I have an initial energy, it's 0. I have a final energy, it's 0.54. Let's plug those numbers in. And now we see that the net work is equal to positive 0.54 joules, which is exactly the same answer we got when we calculated change in kinetic energy. That's the work energy theorem. It states that they're equal. The net work done on that system equals the change in KE. So I should be able to solve it either way, and I should get the same answer. Okay, so again, same exact thing we just got a moment ago. All right, so we talked about positive work and negative work, and we've talked about them a few times, but I want to revisit it because it obviously shows up in this equation. So let's just remind ourselves that positive work is done when work adds energy to a system. So if you have a scenario where energy is being added to the system, that is going to be positive work. For example, a desk is initially at rest before it is pushed for 5 meters with 60 newtons of force, giving it a speed of 3 meters per second. That's a scenario where we push a desk and give it energy. So the work we do adds energy to that desk. Now it's moving. Okay, that would be positive work. The energy of the desk came from the work done. We could write our energy transfer equation. That's our initial energy, which is 0. Plus our net work equals our final energy, which is, in this case, kinetic energy. And so I could write my equation like this. Net work equals KE final. That would be a shorter way to put that. Okay, but that work that I do will equal the kinetic energy that I have at the end. But that is your energy transfer equation. And again, that's positive work. In the warm-up, gravity did positive work. Okay, it caused the kinetic energy of that cup to increase. The force that gravity applied was in the same direction as the displacement. Could have looked at it either way. Negative work is done when energy is removed from the system. So if you do work on something to remove energy, or if something does work on a system to remove energy, we say that that work is negative. For example, a 0.5 kilogram ball initially moving at 4 meters per second rolls to a stop after 7 meters due to friction. Well, guess what? We had kinetic energy and now we don't. Now it's stopped. Okay, and that is because friction did negative work on the system. Friction removed energy from the system. Okay, guys, if you have negative work, that negative work is going to cause energy to be dissipated from the system. And y'all need to know this term, dissipated energy, because you're going to see it again. It's on my next slide also. But when I say energy is dissipated, when you have friction, okay, like if you rub your hands together, that's like the common example they teach you about friction in like elementary school, you get heat. Same thing. Okay, if you have something being pulled across the ground and rubbing against the ground, or a ball rolling across the ground, there is energy dissipated, meaning that energy is no longer mechanical energy that the ball can use. It's now in the surroundings. It's heat on the floor. Okay, again, it's not necessarily a noticeable amount of it, but it's there. It's dissipated to the air molecules, it's dissipated to the floor. That energy has left. A lot of times it's heat, sometimes it's sound, sometimes it's light. There are different types of energy depending on the scenario, but they're no longer useful. Those are dissipated energy. And the kinetic energy of the ball, in this case, all of it gets dissipated because it's not moving anymore due to that negative work. And so we can write that equation in two different ways. We can say that initial kinetic energy plus the net work will equal 0 because we don't have any energy at the end. Or we could say that our initial kinetic energy all gets dissipated. It's equal to our dissipated energy at the end. And the reason I'm introducing this term is because there are about 3 different ways, maybe more, but at least 3 different ways we can ask you the same question. I could ask you in this scenario, I could say, hey, there's this ball rolling at 4 meters per second. It comes to a stop after 7 meters due to friction. What is the work done by friction? You could solve for it that way. Instead of wording it like that, though, I could say, what is the change in kinetic energy of the ball? Same question, same answer. Or I could say, what is the energy dissipated due to friction? Same answer. It's 3 different ways of asking the same question. Okay, so if you see that, I just want you to be aware of it. Let me give you a better definition. Okay, in an open system, energy is often dissipated or lost from the system, so it's no longer available to do work. Okay, you could have a sled that loses energy because it slows down. My previous slide was a ball. I think I should change this to ball. But the ball in the previous slide loses kinetic energy due to friction, which would generate things like heat or sound. The energy still exists, it's just no longer useful. And so we say that it's dissipated. The amount of work done by friction will equal the amount of energy dissipated from the system. So again, you will get the same answer no matter which way we phrase the question. You're going to solve for it the same way. All right, let's look at an example. Okay, again, I would recommend that you write some of these down. We're going to have, I think 3 examples in here. But this one says a custodian pushes a 25 kilogram desk from rest along a horizontal surface until it reaches a speed of 3.5 meters per second. What is the work done on the desk? Again, start by labeling. My mass is 25 kilograms. It's from rest, so the initial velocity is 0. It reaches a new velocity, a final velocity of 3.5 meters per second, and we are looking for work. Now, if I look at my equation for work that we learned last week, it's force times displacement times cosine theta if I have an angle. I don't have any of that information. I don't know the force. I don't know the displacement. There is no angle. Okay, and so I can't use that equation. Instead, we're going to have to use the work-energy theorem because although I don't know the force or the displacement, I do know that work is also equal to the change in kinetic energy. And I've got a mass and I've got some velocities. So I'm going to use that equation instead. We're going to write the equation though. This is the standard equation. Initial energy plus net work equals final energy. But we're going to be more specific. Our initial energy is kinetic. Our final energy is kinetic. So we're going to write it like that. And by the way, my initial energy, 0, wasn't moving. Okay, so I can write my equation like this instead. My initial kinetic energy, 0, plus the net work done will equal the final kinetic energy. Now, could you do this in pieces like we did the warm-up? Yes, you could. You could take those numbers and say, okay, here's my initial KE, here's my final KE, let me find work. But if you can write the equation like this, you can do it in one step. You don't have to solve it in pieces. Okay, now you'll notice I don't have a kinetic energy over here. I have a mass and a velocity. So I'm going to substitute in, instead of KE, I'm going to substitute in 1/2 mv squared. Now I really can do it in one step. Okay, and so that's my equation. Here's my 0 plus my work, and you don't really have to write this 0. Work equals 1/2 mass velocity squared. Okay, if you multiply those out, you get positive 153.125 joules, and that is the work done on the desk by the custodian. The custodian gave it more velocity, added energy to the system. The work is positive. And what I solved for wasn't really work. I solved for kinetic energy, but that's where it came from. And I know that because of the work-energy theorem. Questions about this example? All right, let's look at another one. A 0.65 kilogram ball rolls with a velocity of positive 4.1 meters per second when it rolls over a 2.8 meter rough surface with a frictional force of 1.15 newtons. What is the final velocity of the ball? Let's list our givens. We have a mass, we have an initial velocity, we have a displacement, and we have a force. However, I know when I see friction that it needs to be in the opposite direction as the motion of the object. The object's motion is positive 4.1 meters per second. Therefore, when I write my friction, I'm going to put a negative sign in front of it because friction is always opposite the direction of the motion of my object. So it needs to be negative because my velocity is positive. Don't forget that sign. It'll mess you up if you forget it. All right. I'm trying to find final velocity. And I don't have enough information to do it with these equations on my board, at least not in a single step. When you look at these problems where you're looking at a situation where you have energy that changes due to work, always go back to writing your own equation using the work-energy theorem. That's where we start. Okay, so if you have a scenario where you have energy, there's some kind of work that's done, and then energy, okay, or even if one of them's 0, this is the equation you start with. My initial energy is kinetic because I'm moving. Positive 4.1 meters per second. I have an initial velocity. I have KE. Okay, work is done by friction. It says it in the question. And my final velocity of the ball, that means it's implying that I'm still moving at the end. So we could write it like this. KE initial plus work done by friction equals KE final. I'm expecting it to slow down. But again, I don't have KE. Now, could you solve these pieces? Sure, you could. But I'm going to go ahead and substitute in the variables for KE. KE is 1/2 mv squared. So I'm going to do this. 1/2 mv squared initial plus my work done by friction. I have an equation for work, force times displacement. I put that in there because I don't know the work, I know the force and the displacement. I can find the work. Equals 1/2 mv squared final. So instead of leaving all those other variables in there, KE, work, KE, I went ahead and put variables I can actually use. Again, you don't have to do it all in one step, but this is going to make your life easier if you can do it. Okay, practice it. Substituting in looks like this. It's kind of long. It doesn't fit on one line. But I have 1/2 times 0.65 times 4.1 squared. That's my initial kinetic energy. Plus my work done by friction, negative 1.15 times 2.8. Equals my final kinetic energy, 1/2 times 0.65 times VF squared. So this whole left side of my equation, this part up here, 1/2 times 0.65 times 4.1 squared plus negative 1.15 times 2.8, I'm going to go ahead and solve this side. The whole left side is actually equal to 2.24. Okay, so now I have 2.24 equals 1/2 times 0.65 times V squared. We need to move that half of 0.65 to the other side. So I'm going to divide both sides by 1/2, and I'm going to divide both sides by 0.65, and that's going to give me this. 6.9023, you can write all the decimals if you want, equals V squared, VF squared. But again, I want VF, not VF squared, so we're going to take the square root of that, and we get our final velocity is 2.63 meters per second. It slowed down. It was 4.1, now it's 2.63. I already knew that. Friction does that. Okay, so that's my final velocity of the ball. I'm going to ask you a follow-up question, but before I do that, does anybody have a question about this? Okay. Follow-up question, how much energy is dissipated due to friction? How much energy does my ball lose? Okay, and again, if I want to find dissipated energy, that's my energy loss due to that negative work. This is one way I could word the question. That's why I showed you guys dissipated energy a minute ago. So let's write our own equation. Initial energy plus that work, again, that's where that dissipated energy is going to happen, equals final energy. Again, my initial energy is KE plus work equals KE final, but I don't have KE, I have these variables instead. Okay, I don't want to solve for force or displacement here. I just want the work, so I did not substitute those variables in. If I can determine how much work is done, I know that that's my energy dissipated. So let's substitute into this equation, and we get 1/2 times 0.65 times 4.1 squared. That's my initial kinetic energy, plus my work equals my final kinetic energy, which is 1/2 times 0.65 times 2.63 squared. So here's my initial KE, 5.463 plus work equals 2.248. If I want to solve for my work, I'm going to subtract 5.463 from both sides, and my work is negative 3.22 joules. That is how much energy was removed by friction, and therefore the energy dissipated is 3.22 joules of dissipated energy. Again, it's another way of asking the same question. Now this, frankly, is a longer way to answer it. There's at least two different ways. I'm going to show you another one. This is one way to go about it, but we just said that it's equal to work. Why not just solve for the work? We could do this. We could find our initial KE, our final KE. That's what we've been doing, changing kinetic energy. That's going to be my answer. Okay, we could do that. Or we could just solve for the work, because that dissipated energy is equal to the work done by friction, which is equal to force times displacement, and we have force and we have displacement. So that dissipated energy equals negative 1.15 times 2.8, which guess what is exactly the same answer that we found a second ago. It's still negative 3.22 joules of energy loss, and therefore 3.22 joules of dissipated energy.
So if something like ends at like a final velocity of 0,
then all of the energy would be dissipated, yeah. If you didn't hear her, she said if it ends at a final velocity of 0 and I asked for dissipated energy, it would be all of it. All right, any other questions? Again, I can ask for dissipated energy, work done by friction, change in kinetic energy. They're all the same answer. Okay, they're all asking for the same thing. All right, that's what you're going to be doing in today's assignment. Again, it's 601.3 work energy theorem problem set. You have the remainder of the class period to work on it, which is 23 minutes. So you have plenty of time to work through at least a few of them so that you're able to ask for help if you're not sure what's going on. Another reminder is that your RA is due tomorrow by 11:59 p.m. That's another thing you could look at, is the extension questions are also similar to what we just did. Lastly, guys, there's a note at the bottom of my screen. The YouTube playlist where we put the video lectures now has video solutions for 601.1 and 601.2. In case you had trouble with those and want to go back and look at it, you can do that. Okay, there will be one posted for 601.3, but not today. Okay, so y'all got to do that on your own today, or ask for help while you're in here. If you have questions as you're working, please let me know.